Hello, I'm Berenice Baker, the editor of Enter Quantum. I'm here with Dr. Todd Tilma, a quantum evangelist with Continuum, based out of Japan. Hello, Todd.
Hi, Bernice. How are you today?
Very well, thanks. I wonder if you could start by please giving us an introduction to Quantinuum and your role there.
Sure. So, Quantinuum is the world's largest integrated quantum computing company. It's formed by the combination of Honeywell's quantum solutions, world-leading hardware and ion trapping, and Cambridge Quantum's class-leading middleware and application software. We employ around 400 people, including 300 scientists at 7 sites in the United States, Europe, and Japan. And we're constantly on the lookout for new talent, new collaborators, new ideas, because to us, there are no competitors, just colleagues. Our motto is science-led and enterprise-driven. And Quantinuum has decided to accelerate quantum computing and the development of applications across chemistry, cybersecurity, finance, and machine optimization. Our focus really is to create scalable and commercial quantum solutions to solve the world's most pressing problems in fields such as energy, logistics, climate change, even health. Now, how we do this is through the creation of user-centered products. For example, Quantinuum's open source development toolkit, called Ticket, provides platform-inclusive access to the world's leading quantum hardware and simulators, as well as enhances the performance of every Quantinuum product. It's our cornerstone of how we develop. It's part of our cybersecurity key generation platform, which we call Quantum Origin. It's part of our quantum computational chemistry and material science package that we'll talk about later, which we now have named InQuanto. And it's part of our moonshot program, LAMBEC. It's Quantinuum's quantum natural language processing and computational linguistics toolkit. Furthermore, on the hardware side, Quantinuum's H1 series of ion traps, or quantum computers, they're powered by Honeywell, are one of the most advanced in the world. And they were the first to pass the industry standard quantum volume of 2048 benchmark just recently. And we are committed to an interesting, and I almost say very gutsy position of increasing the quantum volume of its commercial computers by orders of magnitude each year for the next 5 years. Now, as for me, as a quantum evangelist, there's 4 of us. In Quantinuum, my role is very simple. It is to evangelize our mission, or put succinctly by our CEO, Ilyas Khan, to positively change the world through the application of quantum computing. I try to do this by sharing our corporate ideals, research and technological insights that we may make, and, which may sound kind of strange, our employees' hopes and dreams to whomever will listen. I'm a former academic, and so I try to follow the lessons laid down decades ago by Guy Kawasaki. And I read his books, Selling the Dream, The Macintosh Way. I don't know if you can even see it. My apologies. These are great books for learning how to be an evangelist. He was the first, in a sense. And what they say is inspire. Do not compete. We run by a quote. I believe in this. And if you join me in this belief, it's going to be great for all of us. So, more explicitly, I see my job as in really learning about our products' unique features, helping our sales teams explain these features into useful benefits to our clients. And most importantly, communicate to the public at large that these products that I've just earlier mentioned are actually designed from the bottom up to improve the quality of everyone's life. It's kind of a strange thing to say, but I really love what I do because I believe in the inherent positivity that quantum technologies will bring to the world.
That's really inspiring. Thank you so much for that, Todd. So you touched on in Quanto earlier that performing complex chemistry problems is one of the most important use cases for quantum computing. So earlier this month, Quantinuum introduced in Quanto software platform. Could you explain how it will make using quantum computing easier for chemists, please?
Oh, yeah, that's excellent. It's an excellent question because it's an excellent issue right now. When you talk to chemists today, you inevitably hear about the problem of accurately and efficiently prototyping a molecule or understanding the properties of a new material. And what I mean about that is modern chemistry today is more and more now done using computational resources rather than wet labs. And in computational chemistry, there are two major challenges. The first one is that current technologies, current high-performance computing systems, and current software uses techniques such as density functional theory. And these are great. It's a great theory, but it uses approximation to reduce the computational complexity. But by reducing the computational complexity, you lose accuracy. Or you can go to highly accurate techniques. In particular, there's something called the correlated wave function methodology. Now, these exist, but they impose heavy computational overhead. So much so that these scale very quickly past what industrial relevant problems can solve, and they actually become almost intractable to our current level of HPC. Even at the exascale level, these become very, very difficult problems. So we believe that quantum computing promises to make that second idea, that second concept, that wave function, correlated wave function theory method, affordable to the computational chemist. Now, what do I mean by affordable? I mean affordable in time. They can do it. It shortens their time from start to finish of programming. Affordable in computational resources. They don't have to go get large amounts of servers. And most importantly, affordable in the overall return on investment or return on investment. The amount of upfront cost will be returned back to them 100-fold. Now, our new and quantum software package maps a quantum system, in this case it's a molecule or a material, to a programmable quantum system, the quantum computer. This is Feynman's original idea back from the early 80s. In this way, the wave function-based algorithms, those very, very accurate but computationally, has high overhead, may be efficiently implemented. Now, I say maybe because to reach the chemical accuracy at cheaper cost in the future that we are striving for, we're going to need larger quantum computers. Okay, so with that said, why release in Quanto now when we do not have full-scale, fault-tolerant, error-corrected quantum computers? Because the current era, this noisy intermediate scale quantum, NISQ device era, is ideally suited for testing and prototyping these quantum chemistry algorithms and methods. We can't run yet, but we're crawling. And when you're crawling, you start learning how to balance yourself for walking. And so we're at that level of testing out, and what we learn now will help us in our future designs. We believe it is essential to prototype today with real-world use cases, no toy models, so that methods are tailored to solving industrial relevant problems. For this reason, we've created in Quantum platform. It's a platform, actually. It's a full functioning platform to enable users, not just the computational chemists, now these material informatics people, even just quantum developers, people who are in quantum computing, but they need to start thinking about materials science, to easily experiment with the latest quantum algorithms and techniques on a range of quantum backends to help them understand the potential of quantum computing to significantly improve the accuracy of complex molecular material simulations in their field. Now, I'm going to continue talking if you don't mind. It's a lot here on Inquanto. And why I want to talk about Inquanto for a bit is, you see, it's a Python-based platform. Most of our material is Python-based. That allows us to program, or allows anyone, in their familiar Jupyter environment. So again, a lot of open source material here. Inquanto uses our open source software development ticket to enable users to seamlessly transition their code onto actual quantum hardware or simulation. Okay. The platform itself, so when you buy a license, you get the main package, which is titled Inquanto, various extensions, the ticket backend, and the main package itself also has the latest and most relevant NISQ algorithms for quantum chemistry. So it's effectively an end-to-end approach that supports both molecular and periodic systems. And the way we designed it, no, not me, but the way our corporation designed it, was that it was a mix and match philosophy. I could take a little from here, various algorithms, a little bit here from circuit synthesis, measurement reduction methods, so that I can ensure that the simulation will run on early stage devices, be it Rigetti or IBM or us. And those simulations, those real simulations, would be realistically sized molecules or solids. I mean, we're trying to get it out now for testing. And if you're curious, as a brief bit of an advertisement here, and you want to request a demonstration, you can go to our website. It's www.quantinuum, as you can see there in the little corner there, .com, products, Inquanto. And I'm going to spell it out because for all of our Italian listeners, it's not Inquanto, it's INQUANTO. So I always love that last part.
That's fantastic. I'm sure that's going to be really useful for our readers. Thank you. So the other big news out of Continuum is that last week you introduced an upgrade to your H11 ion trap computer from 12 to 20 fully connected qubits. So what's the significance of this?
Well, first off, I got to say, we got 20. And I know many people would go, yeah, but IBM's over here with this or that. So I would like to start my response, my answer, by repeating what Tony Utley, our president and chief operations officer, said about the upgrade. With these upgrades, and it's these, so there's more than meets the eye here, developers are able to run more complex calculations than they could before without sacrificing performance. This upgrade is yet another example of our unique business model of continuously upgrading our systems even after they are in commercial use to provide the best performance to our users. And this is true. We will be continuously upgrading even after you have it so that we offer the best user experience possible. And, the upgrade itself is really quite amazing from a technical standpoint. Now, there's a lot I can't talk about, obviously. We don't want to give away the secret sauce. But our director of commercial operations noted earlier this week that the biggest, or maybe the most notable, is that we expanded the number of fully connected, as you said, from 12 to 20. And it's a significant increase in the most that we've ever done to any machine. Now, last year, we added 2 fully to 10, and we thought that was hard. But now it seems easy compared to how we did this. And what we did is, well, we didn't just add more ions. We just didn't dump ions into the trap. In order to add 8 more fully connected qubits, maintain all-to-all connectivity, we upgraded the optics to deliver the light used to control the qubits. Now, the light is visible. Okay, so we use visible light frequencies to control our qubits. This optical upgrade meant that we had to do a complete redesign of the entire optical delivery system.
Wow.
Yeah, right? It's like, I'm just going to add a few qubits. The optics people went, and it's a redesign. This was necessary, though. You see, so it's not to deliver light to more regions of the trap, but to improve stability. And this is the power of the design of the Honeywell H1 series. Previously, we were only delivering the light needed to complete quantum gates in 3 different regions of the trap. And we call these gate zones. So we have zones where we move the ions and then we apply the light, and that does our gate operations. But the trap has 5 zones. Now we can address all 5 simultaneously, thus the requirement for the redesign. This enables us to complete more single qubit operations, more 2-qubit gates in parallel. So by default, you can automatically program in more complex algorithms without experiencing an overall slowdown. Lastly, as Brian, he noted, the gate zones are where all the interesting quantum stuff happens. And more zones allow us to run more quantum operations in parallel. Faster, more complex algorithms. So that's a lot of words. That's a lot of talking. So let me bullet point it for everybody here, because that's really what they want to know. We've got 20 fully connected qubits. We've preserved our low 2-qubit gate error. So for the past 2 years, we've preserved that level that we've kept. We've maintained our high fidelities at 99.7, 99.8% per gate. We've increased our effective gate zones now for parallel operations. But most importantly, and this is what got me excited, is that the performance of the machine was verified on industrial real-world problems by J.P. Morgan Chase and others. And let me just finish with a quote from Jim Walker. He's our principal quantum engineer and part of the upgrade. With the upgrade of our H1 series quantum computers to 20 qubits, our customers are going to continue to experience world-class quantum performance at even larger scales, which will allow them to push the envelope and achieve even more things that they haven't even done before. Now, if you want more information, I highly recommend going to our website, again, www.quantinuum.com, and it's /N20. But a little note, there's no quantum volume listed yet. Please don't ask, because they don't tell me. They're smart, and I'm sure if you start asking them, they'll go. So don't ask, because we don't know right now. But more importantly is that it's the 20 qubit fully connected machine that was just tested with an industrial level problem by JP Morgan.
That's a beautifully clear explanation. Thank you so much, Todd. And you touched on JP Morgan Chase just there. So their researchers released a paper showcasing work performed on the upgraded H11. Can you tell me a little about what they found, please?
Now, I'm going to get a little difficult for you. My apologies in advance. As I was not part of the research, I don't want to comment on the paper itself. I believe that always should be left to the authors themselves. As a former academic, With that said, I can say a few things. The first one is that Dr. Pistoia's team at JP Morgan Chase has become the world leader in quantum information research and development. And we are really extremely proud to have been a partner in this latest work of theirs. Now, here's why. You see, Number one, before I get into their actual research, I need to re-emphasize the importance of that their work is groundbreaking, but it could not have occurred without the all-to-all connectivity that the H11 system brought to bear on the problem. Furthermore, in the past, colleagues of mine even have studied theoretical problems, max cut, and other things like that, to test machines. So theoretical problems to test machines. These guys at JP Morgan, I love them. They gave us a real-world problem that, from my reading, honestly, will have a real-world impact. And that's an excellent way to test a machine. Give them a real-world problem. No toy, no theory. This is something we really need to worry about. So, why believe me? I'm the evangelist. That's my job. Dr. Pistoia, my apologies, I mispronounced his name, Pistoia, recently said about his work, the quantum computing team at JP Morgan Chase has been using Quantinuum's quantum computer to run experiments that use mid-circuit measurement, unique for us, and reuse and quantum conditional logic. Three things that we are very proud of with our systems. Taking advantage of the computer's very high quantum volume, as well as uses of all of the 20 qubits, because of the full connectivity, on a quantum natural language processing algorithm for extractive text summarizations. The results are almost identical to the reference values computed with a noiseless simulator, validating the computer's high fidelity as shown in our recent archive preprint. Thanks to this, Quantinuum computer continues to be an essential resource for our research in quantum computing. I'd like to highlight two things before I give the archive post. One is that they did quantum natural language processing. As I mentioned earlier, our software package, Lambec, this is in our computational intelligence and quantum natural language processing. This is in our moonshot. We believe this is something that quantum technologies and quantum information processing can help us with. And JP Morgan has just given a nice example use case of how it can be used. Second, everything about the algorithm, the need for mid-measurement and conditional logic and the high connectivity, that's only possible currently right now with our Honeywell systems. So, in a nutshell, this is groundbreaking research. It supports the development of our hardware, which we're very proud of. But more importantly, it also begins to see a bit of the light at the end of the tunnel for our moonshot of what we think this quantum, natural language processing, what we think quantum computers may be able to do. And so, we work this hard to make these machines because we want people like JP Morgan Chase to do research that will make the world a little bit better. If you want to find the paper, he said it's on the archive. You can also see it. It's on our website. But for those of you who are experienced with archive papers, it's on archive.org /ABS /2206.06290. And I highly recommend reading it. I enjoyed it. It's a wonderful paper.
That's great. So something we discussed last week at the Quantum Summit was we're at such a pivotal point now that finding real-world use cases for quantum computing is super important.
Isn't it? And it's so wonderful when it's this, it's a serious bank and it's a serious issue. And when you read the paper and you go, oh my gosh, they were doing that, you suddenly see why they were doing it. And not to give away the candy store, but let me just say this way. If their results hold and we can make this, extend this out, make it bigger, then a lot of data, a lot of written data becomes much more accessible to us and usable. Not just accessible, usable. That information overload that we talk about today, this is a step toward possibly the development of ways and means to slow that down and actually deliver what we need when we need it in the format that we want.
That's so important. Thank you. So, given the huge leaps Continuum has made over the last year, what are you working on next?
Well, it's kind of a funny question. We always are listening to our customers and the community in order to improve our software and hardware offerings and their overall experience. Ticket, for example, has almost a 2 to 3 week upgrade cycle. We just had a conference, QNLP, that focused on quantum natural language processing. Next week, we'll have another one. So we are constantly doing that. We're constantly engaged in working on bettering our fundamental products, looking at Origin and in cybersecurity, making Ticket the de facto software development kit for the open source community, to make our hardware scalable past 20, getting those quantum volumes, making in Quanto not just available for the big companies, but with, a 3 to 5 year plan where we are developing it and making it accessible to universities and various things. One of the reasons, we have a commercial hardware system now is to allow our customers to program their algorithms on real machines. And that's actually quite important because they're dealing with all the constraints of real quantum hardware. They're pushing their algorithms. By pushing their algorithms, we learn where our hardware fails and where we need to be updating and doing that. So as they learn new things about their algorithms, we learn where the most important things are for us to improve. Everything from the minor changes in how Ticket will transpile for circuits to we need to add another possible additional software package in Quanto, to can we optimize our key generation Origin to make it more usable or user-friendly in different devices and in different areas. So, we learn a lot from our customers, and they're learning a lot by running on our hardware. So, what are we working on next? Everything.
Excellent. I think it really illustrates what an exciting period we're at with quantum computing. So as a quantum evangelist, what excites you the most about the current status of the industry?
Well, that's a hard question. I've been thinking about that for a while. And I think what excites me the most is what I said at the very beginning. When you work with people like Ilyas Khan and Tom Utley, who believe in the positivity, the fundamental goodness that the quantum revolution will bring, it brings out the best in you, and it brings out the best in everybody. And so today, the current status of the industry, I see a lot of people coming out of academia like I did. I retired after 25 years. And a lot of people go out, they become venture capitalists, and so we're going to start our own company and we're going to do this. But you have to have more than just an idea and more than just venture capital. What I like about Ilyas and Tom's belief is that they bluntly say, we answer to no one but ourselves. We're science-led and enterprise-driven. We only publish what we know is true. We listen to our customers. And if we're wrong, we'll say we're wrong. They are really in it for the long term. That's why they always like to say, we're hardware agnostic. We don't bet on anyone. And so what excites me most is when I look out at our collaborators, colleagues, friends. I don't consider, that's a competitor. We need to beat them. I see the beginnings of a very large ecosystem that I want to help generate, and I think it's going to become huge. And I think everyone will benefit. And then let me finish you with this. What excites, what really gets me going, is that this technology is now all available on the cloud. And you don't have to go to a lab like I did when I was an undergraduate, or you don't have to have a lot of money. I mean, you can access it from your phone. And so, isn't it wonderful that today we have a quantum machine and software out there that through YouTube you can learn how to program, and somebody somewhere, maybe in the global south, maybe in Ethiopia, maybe in Brazil, is going to pick up a phone and just start programming, and they're going to be the next Elon Musk. They're going to be the next, Steve Jobs. That's what excites me about the current status of the industry. Is we're at that inflection point from being a company of a few people and big things to everybody in the world is going to be engaged. And wow, I don't think we've ever seen that. And that's what excites me.
That is absolutely fascinating. Thank you so much, Todd. It really is an exciting time.
Thank you, ma'am.
So it's been great talking to you. Thank you very much. And to stay in touch with the latest quantum computing news, please visit enterquantum.com and subscribe to the newsletter. But for now, I say goodbye, Todd. Thank you very much.
Thank you.